All right, everyone, I'm going to make a quick video to help with the review for this test coming up on Friday. I know we went over some stuff today, but I wanted to make sure that we kind of slowed it down a little bit, make sure you caught all of it. The board got a little congested in some of our examples, so I'm going to do a little slower, break it down of what I was doing, and probably color code it out so you can see a little bit more what was going on. So we're talking about series circuits, series electrical circuits. And what a series circuit is, it means that there's only one possible path that current can flow. For instance, if we have a DC voltage source, something like this, when the voltage leaves, or when the current leaves the voltage source, the only possible method to go is in one direction. Now, series circuits can look different. This is a very simplified one. You could make it slightly more complex. In this example right here, if we follow the current flow, we still only have one possible path that the current can flow through. These are going to be series circuits. The one that we'll get into in the next chapter, we don't need to know this for today, so I don't want to get you confused, would be a parallel circuit or a combination, depending on what we look at. Notice in a parallel circuit, there are multiple paths that the current can travel in. So when it leaves the voltage source, it can go through this resistor and return back, or it can leave the voltage source and go through this resistor and return back. In that case, there's more than one path, therefore it is a parallel circuit. So these would be the difference. Right now we're focusing on the series circuits with the current flow, voltage drops, power consumptions, things of that nature. So there were a few things that we said were key to understanding or associating with series circuits. Number one is that there's only one path. Number two is that the current will be equal at all points. This is only true for a series circuit, but no matter if I measure the current here, if I measure here, if I measure here, if I measure here, if I measure here, it doesn't matter. It's going to read the same amount of current at any given state. While I'm on that topic, we talked about the meters and how we use this would be a DC voltage source. So how would we measure the current of a DC voltage source? We physically have to put the meter in the circuit. You can't do it across it with the lead. You have to actually branch off, break the circuit, and put the meter in line with it in order to get an accurate reading of the amperage that's going through the circuit. Now, voltage, when the circuit is connected, we can touch different points and we're going to get different voltage drops, which we'll calculate in a minute. But for current, we have to have the meter in the circuit. Now, since the current will be equal at all points, it doesn't really matter where we put it, we're going to get the same reading. That's important to know. All right, so based on these two rules, there's only one path of current flow makes a series circuit. Current will be equal at all points, and then the total resistance of a series circuit is equal to the sum of all resistors. And the mathematical expression that we use for that would be RT, so the total resistance is going to be equal to the sum of each of the resistors together. It doesn't matter how many resistors are in the circuit, in our case, which are 1, 2, 3, 4, 5 different resistors in there, we would just sum them together. If there were more than 5 or continuing on, you can add them indefinitely. That's usually summed by this of R to the n, meaning however many resistors I have. But simply we just add up those values to get the total resistance. So let's just throw some numbers in here for these values. Let's say that this is 100 ohms. This one is 150 ohms. This one is also 100 ohms. This one is 300. And this one is 500. So back to this equation here, the total resistance, RT, is going to be equal to the sum of all the resistors added together that are in a series circuit. So you notice that we only have one path for current to travel. Therefore, it's a series circuit, this will apply. So in our case, if we just plug these numbers in, the total resistance of this circuit is going to be equal to, and this is R1, R2, R3, R4, R5. It just means the resistor at that location. So R1 is 100, R2 is 150, R3 is 100, R4 is 300, and R5 is 500. If we add those numbers together, we have 100, 200, 350, 650, 1150 if my math is right. So the total resistance, RT, total resistance for this particular series circuit would be 1150 ohms. I'm just gonna double check that real quick. Yes, the total resistance of this complete circuit would be 1150 ohms. I want to make this a little less cluttered so you don't get confused. And what that means is now that we have the total resistance, we can treat this circuit as this equivalent circuit here. This would act just like if I had the same voltage source and one resistor that measured 1150 ohms. So let's say for the sake of this that we're using a 24 volt DC voltage source. This would be the symbol for a battery. So now that we've found the total resistance and we know the voltage source, using Ohm's law we can determine what the total current would be. And based on the rules of a series circuit, it will be equal at all points, so we only need one value. So Ohm's law, this is the easy way that I remembered. I like to use this diagram. If you use the Ohm's law triangle, it says that the voltage V is going to be equal to the current times the resistance. And you can rearrange this formula in any way you want, depending on whether we're solving for current, whether we're solving for resistance, or whether we're solving for voltage. In this particular instance, we're solving for the current. We want to know the current flow through the circuit. And the way you would read this diagram is if I'm looking for current, then it would be voltage divided by resistance. If I were looking for resistance, it would be voltage divided by current. And if I'm looking for voltage, it would be current times resistance. In this case, I want to know what the current is, I, so it would be the voltage, 24 volts, divided by the resistance of 1150 ohms. So if we plug that into the equation where I equals V over R, and since there are multiple resistors in this circuit, I'm going to call this RT, the total resistance value of all the resistors in that circuit. So in this case, the voltage would be 24 volts, and the total resistance would be 1150 ohms. The number that we get in the calculator is going to look like this would be in amps. Very important to remember that the units have to be in their base units. This can't be kilovolts or milli ohms or mega ohms. It needs to be in volts and ohms in order to get amps. But once we get this value, this would be the same as saying 20.8 milliamps. Move the decimal 3 times back, that would be 20.8 milliamps. So the total current in this circuit, in either one really, the equivalent or the original, is 20.8 milliamps. So the current going through this circuit, 20.8 milliamps. And we know from the second rule that the current is equal at all points. The current passing through every single resistor in this series circuit is going to be 20.8 milliamps. So at this point, we now know the voltage source. We know the resistance value of each resistor, the total resistance of the circuit, and the total current passing through. So we're going to call this IT, or the total current of the circuit.